So let's get started. There was a question on Piazza about updating the readings to include the 3rd edition. So I've done that, and that stuff should be live on the group page or on the course website. We're a little bit behind, but I want to take one quick moment to summarize what we talked about last time. Mostly we talked about how shielding concepts can be used to understand the size of atoms and also their ionization energies. It's important to remember that as you go from left to right across, say, the transition metals of the main group elements, and you're filling up d orbitals or you're filling up p orbitals, each subsequent electron does shields the nucleus partially. And so the effective charge that is felt on adding a proton and an electron becomes more and more positive. And this is the origin of why it's harder and harder to pull an electron out or off the atom as you go to left to right. And so fluorine is more electronegative than boron. It's harder to ionize than boron. Nickel is the same. Nickel is harder to ionize than titanium or scandium. Effective nuclear charge also goes up as you go down, so chlorine to iodine. And you might predict that that means the ionization energy should go up, but you have to remember that the ionization energy is also related to the size or the separation between the electron and the nucleus. So the further the electron is from the nucleus, the more easily it's ionized. And so this explains why when you jump from one energy level to the next, you get a sudden change in how easily ionized the atom is. This is the reason why sodium is much more easily ionized than the noble gas just before it. So we also mentioned a couple of other kind of fun facts about that. One is that when you first fill up the d orbitals and then you move into the main group after filling up the d orbitals, there is an unusual contraction that happens called the Scandide contraction, where gallium is unusually small compared to, say, what it would be without that. So gallium turns out it's about the same size as aluminum. Germanium is about the same size as silicon. And that's largely because of this d orbital block filling up and the charge not being very well screened. The same happens in the lanthanides. You fill up the lanthanides, f orbitals are terrible at screening charge because they don't penetrate to the nucleus at all. So there's this big jump in effective nuclear charge, and the 5D transition metals are abnormally small. They're the same size as the 4D transition metals. There's also relativistic effects involved. Elements that large have electrons that are contracted, and that contraction contributes to this change in radius. And all of that helps to make 5D transition metals unusually good at bonding. Small atoms do a better job at bonding. And so there's greater covalency in the 5D transition metals than you might expect. And that's one explanation for why they're nice to work with and less reactive, sort of easier to control elements. So we'll come back to that. So just briefly, I'll mention, well, I guess I've talked about this. The electronegativity goes up as you go from boron to fluorine. It goes down as you go from fluorine to astatine. So remember, electronegativity, well, I've got to share my screen here. Okay. What is electronegativity? Of course, you know that electronegativity is a measure of an atom's ability to attract electrons to it. And so to which it's bonded, and it generally parallels ionization energy. Okay, there's a nice figure. It's figure 8.2 in the 5th edition. It's a table that looks a little bit like this here. I don't know how well you can see that, but it's this sort of cool graph illustrating the electronegativity of the elements as this sort of bar chart. And so you can go take a look at that if you want. Illustrates this stuff very cleanly. So electronegativity goes up as you go boron to fluorine. Said that over and over again. It goes down as you go fluorine to astatine. What does it do as you go scandium to nickel? Who's more electronegative, nickel or scandium? Got to know your periodic table to answer that one. I hope you guys are putting some effort into doing those exercises because you need to know your periodic table. Who knows where nickel is?
Should be nickel.
Nickel is more electronegative than scandium because it is located where?
On the rightmost end of the top row for the transition metals.
Yeah, it's in the upper right-hand corner. Nickel, palladium, platinum. That's a good one to remember. Nickel, palladium, platinum is the rightmost group. It's D10, full set of d electrons. The noble metals there. They define the edge of them anyway. So scandium is a less electronegative. It's like boron, nickel's like fluorine. So nickel goes up as you go scandium to nickel. And gallium and germanium are exceptions. Why is that? Because of the scandide contraction. They have a similar electronegativity to aluminum. And silicon. Right? Gallium and germanium are after the first D shell. So you get this unusually high electronegativity. Okay, so let's move on now.
Is that also the case for the lanthanide contraction as well for hafnium and tantalum?
Yes, although I don't know how often people really sincerely talk about the detailed analysis of the electronegativity of transition metals, but that's the right idea. And so I would guess that this is true. All right, so we're gonna switch gears a little bit. How do we do this? There we go. We're gonna talk about Lewis structures and VSEPR. Wow. Apparently I don't do so well with the keyboard on this thing. Structure. Probably should have written it out. Structures. Let's see here. Structures. There we go. Great. All right. So let me just say something briefly about Lewis structures and VSEPR. Inorganic chemists have to draw complicated electronic structures when they draw molecules, more so than organic chemists, more so than biochemists. And so they have gone to great lengths to develop rigorous structure drawing formalisms. And most chemists do a poor job of this, I would say. Not most, but many. And inorganic chemists are self-righteous about it. They like to criticize organic chemists for their representation of transition metals, sometimes. And I guess for those of you that feel like, I did this in Gen Chem, why are we doing this now? Let me just say that I want you to take this very seriously, if you can, because I want you to be very good at drawing molecules in a way that is clear and easy to understand, okay? And the rules that you're going to be taught, you really should try hard to follow. It eliminates a lot of confusion. And you know, the homework set, there are these explicit instructions about what to do and what not to do, and I'm going to do my best to be clear about that in the notes today. And I ask that you really try your best to adapt this way of treating the drawing of molecules, and you know, be as rigorous as you possibly can. And do not be annoyed if you do not follow the rules on the homework set and then you get a poor grade. Okay, so I'm going to be we're trying to be rigorous here, and so I ask that you do your best to plug in and try and understand what we're trying to say. So Lewis structures and VSEPR, this is a system of drawing in accordance with the octet rule. Okay. It helps you achieve closed shell molecules. What's a closed shell molecule? It's a molecule where all the orbitals are filled by making covalent bonds. So in the main group, this is the octet rule. There's an equivalent rule in the transition metal series called the 18 electron rule. We're going to talk more about the 18 electron rule later. Both of them seek to fill up the valence orbitals of the metal. Okay. So let's take a look at oxygen to polonium. This is as an electron configuration of 2 electrons in an s orbital and 4 electrons in a p orbital, depending upon which element you're talking about. So there are 6 valence electrons. And so let's do sulfur, for example. Need to be a little more careful here to use my pen well. We have 6 valence electrons around sulfur. And you can take those 6 valence electrons and add 2 hydrogen atoms to get to a closed shell molecule here. So this, we're going to make bonds to fill valence shell. Okay, so in this depiction here, this bond, as we've drawn it, contains 2 electrons in it. And then, of course, there are these lone pairs here. And so if we look at each atom, you can see that this hydrogen atom has 2 valence electrons in this bond, right? The sulfur has 2 bonds, 2 lone pairs. So the sulfur has 8 valence electrons. And these individual atoms then have their shells filled. Okay, so the H atom has a filled sulfur atom has a filled shell, 2s2, no, not 2, sorry, 3s2, 3p6. Okay. So let's do this again. This time we're going to do nitrogen to bismuth. All right. So again, you've got a noble gas core, plus you've got 2 s electrons, and you have 3 p electrons. So 5 total. So let's do it with arsenic. Oops, got ahead of myself. Let's start out by drawing its 5 valence electrons. Okay, and then we're going to make bonds. We use 3 hydrogen atoms. We end up with arsine. Terrible substance. So we 3 hydrogen atoms to fill the valence shell. Okay. And again, you have H atom's got a filled shell, and the arsenic atom has a filled shell because arsenic's got this lone pair and 1, 2, 3 bond pairs around it for a total of 8 electrons. So arsenic's got its octet, and the hydrogens have their 2 1s electrons, so they're all filled. Okay, so the valence electron count on arsenic is 3 bonds plus 1 lone pair equals 8 electrons, right? Each of these has 2 electrons. Okay, so this all makes sense, but you know, some of you are going to stop and have to pause to do this as you go through the assignment. Trying to get to 8 electrons. If you got 5, you need 3 more. If you got 2, you need 6 more. Okay. All right. Now, this bond, as drawn here by a stick, is what we're going to call a normal covalent bond. And this is a bond where 1 electron is contributed by each of the 2 elements that make up the interaction, okay? All right, so one from arsenic, one from hydrogen get together. Duh, that makes sense, but we're assuming a neutral fragment when we do that, okay? We're gonna come back to that. But that's how you think about a normal covalent bond, okay? Now arsine here, arsenic trihydride, is the arsenic and arsenic trihydride is said to be trivalent in this drawing. It's trivalent because it uses 3 electrons to make bonds. Okay, that's what valence means. Valence is the number of electrons used to make bonds. You're gonna run into other definitions, but the most rigorous one, number of electrons used to make bonds. Okay, and you can calculate that by taking the number of electrons in the valence shell. Eesh. And subtract the number of non-bonding electrons. Okay, so arsenic has 5 valence electrons. And ASH3 has 1 lone pair, which is 2 valence electrons. So 5 minus 3, sorry, minus 3, silly. Minus 2 equals 3. So arsenic in ASH3 is trivalent. Okay? Easy. Now, there are these things called hypervalent molecules. Hypervalent molecule. Well, a good one here is phosphorus pentafluoride. Another good one. Sulfur hexafluoride. Now I'm drawing these in a way that illustrates all of the lone pairs present, which is going to be important to do. Okay. And sulfur hexafluoride is a real interesting one. It seems like I don't know. I look at that molecule and I think, oof, that stuff looks nasty. But a friend of mine had his retina detached from the back of his eye, and they did this surgery on him. And for some reason, after it was done, they inflated his eye with sulfur hexafluoride. And it's an unusually inert substance, it turns out. So let's do the math here on sulfur hexafluoride. You know, any one of these fluorines has got 1, 2, 3, 4, 5, 6 lone pairs, or electrons in lone pairs. So 3 lone pairs and 1 bond pair. So fluorine has an octet, right? How about sulfur? 1, 2, 3, 4, 5, 6. Sulfur has 6 bond pairs, equals 12 valence electrons. Okay, phosphorus over here, same story. You got 5 bond pairs and 10 valence electrons. Okay, and so these drawings here violate the octet rule. These molecules appear to violate the octet rule. And what I'm going to tell you is that it's the drawing that's the problem, not the molecule. Okay, and so what are we going to do about that? So I'm just going to make a note here. Now you must be thinking, all right, well, I draw stuff like this all the time. And I'm telling you, for the purposes of the homework, you should not. Okay, the homework instructions say, do not violate the octet rule. So if you draw these structures on your homework as an answer, you'll be marked wrong. So what do we do about that? Let's just first calculate the valence. So what is the valence of phosphorus in the structure on the left? It's pentavalent. Sulfur has 6 valence electrons minus 0 non-bonding equals hexavalent. Okay, phosphorus uses all 5 electrons to make bonds here, and sulfur uses all 6, and so that makes phosphorus pentavalent and sulfur hexavalent.
I have a question.
Yes.
So just like for how we're defining things, because right above you have written that sulfur has 12 valence electrons and that the phosphorus has 10, and then
right. So this is the number of valence electrons in the neutral atom on the bottom, and this is the number of valence electrons in the closed shell molecule in the upper right.
Okay, thanks.
Yeah, that's maybe confusing. Thank you for pointing that out. Okay, so how do these molecules exist? These molecules exist whether or not we understand them, I would say, first of all. It's maybe a bad question, but hypervalency generally in the past was explained using more complicated hybridization schemes where they borrowed orbitals from higher energy levels. Okay, so the octet rule is really just a statement about which orbitals can participate in making bonds. It's really just the primary valence shell composed of the S's and P's and the third energy level in the case of phosphorus and sulfur that can participate in bonding. So you can't go beyond 8. And if you want to go beyond 8, then you have to get into d orbitals or s orbitals of the next energy level. And so that's kind of how people described this stuff in the past, but These days, calculations say that doesn't happen. Those orbitals are too high in energy. They don't really mix in. That's not a viable explanation for this stuff. So what is the explanation? Well, people have written papers about what's called natural resonance theory, which is just a different way to describe things. And it helps us to develop rigorous drawing rules. Okay, so natural resonance theory. It mixes in electrostatic interactions. Okay, so let's do phosphorus pentafluoride. So I'm going to just put a and now for this last one, so here I've drawn 4 bonds. That gives my phosphorus an octet. And now I'm going to draw the last fluorine with an octet. And I'm going to draw this dotted line down to the phosphorus. We're going to give this guy a negative charge. We're going to give that guy a positive charge. And the reason it's drawn like this is to say that the electron pair that was in that bond is now on the fluorine. And so you've ionized the phosphorus in a sense. And we indicate that here with these formal charges. Okay, so no longer making a normal covalent bond here. And so this kind of saves the day. And now we can stick to our octet rule. Okay. Now, there's a lot of ways to draw this stuff out. You might imagine there are 5 different fluorines. And so another way to depict phosphorus pentafluoride is like this. Right? Give that guy his appropriate charge. You can see that there are 5 of these resonance depictions.
Professor Owen.
Yes.
So with the hybridization that's supposed to be, how can you have the dipole not on the axis, but equatorially?
Yeah, so let me say a couple of things about that. I like your question a lot. The first thing here is that the shape of the molecule is not being depicted in these drawings. Okay, it does look like that, and I should have maybe drawn it more carefully to not make it look like a trigonal bipyramid or a square pyramid or whatever. These kinds of resonance theory drawings are supposed to be shape agnostic. Okay, and so 5 of these resonance structures are equivalent in the world where all 5 bonds are equivalent. The molecule, of course, has a shape, and the different bonds are different, and so the resonance structures are not quite equivalent. For the purposes of the class and to keep things simple, We don't need to mix the resonance depictions, the natural resonance theory depictions, and the shape. Okay.
Okay, so
I'm
this
just
is
gonna
just
say-
for like Lewis structures, we'll just always say that they're completely equivalent.
Yeah. Now, this gets a little bit tricky, particularly when you start in considering multiple bonds. Okay, and we'll come back to that issue. But you know, we're not going to get too crazy about cases where it's a little bit ambiguous. For the purposes of the natural resonance theory treatment here, we're going to say there are 5 of these structures and not specify how shape impacts it. Okay, and we're just going to ignore the molecule shape for now. All right, so let's talk about how to draw things. And let's see here. I have a handout. I'm not gonna bring it up and show it to you right now. I'm gonna stick it in the notes, but it gives you an approach for drawing stuff rigorously. Okay, so step 1, begin by drawing a single bonded structure. And by this, I mean, you know, normal covalent bonds and natural resonance theory types of interaction. So you can get up to octets and then, you know, switch over to natural resonance theory depictions after that. You can add pi bonds or double bonds to ensure that you have an octet. Add lone pairs. And then finally, add formal charges. So let's do this for some examples, okay? We're gonna jump ahead to a new page. And what we're gonna do is the SO4 2- ion, okay? So I'm gonna try and, I think I can squeeze these in. I'm gonna start off with a sulfur here. And I'm gonna draw a singly bonded set of oxygens around it. And notice I have an octet here for my sulfur. And I'm going to start putting in some lone, let's see, what did I just say in my order? That's right. Begin by drawing singly bonded structure. I've got to add pi bonds to ensure the valence of each atom is filled, then add lone pairs. All right, so I've got the valence of my sulfur filled. And I need to get to an octet here. So I'm going to put some lone pairs around these oxygens to get to my octet. Right. And now I need to add some formal charges. Okay, so oxygen I know tends to make 2 bonds, you know, H2O, right? Whenever you're trying to remember, just add hydrogens in your mind's eye. That's how many normal bonds you make. Pull off an H plus to leave a lone pair behind, and you get a negative charge by pulling off that H plus. All right, so we have an oxygen here with 1 bond to sulfur, and then nothing else, an electron pair instead. And so this guy has to have a -1 charge. Write a minus, and all of these are going to get minuses. Now sulfur started off with 6 electrons, And now it has 8 electrons in its valence shell in making those bonds. And 2 of those electrons actually ended up out on the oxygens, and this molecule overall has a 2- charge, right? So if you do the math on adding those things up, the easiest way is just to count the formal charge on the sulfate and the number we've already drawn here, right? So we have 4 negative charges, but this thing is supposed to be 2- overall. So to neutralize those 4 negative charges down to a 2-, we better have a 2+ here on the sulfur. Okay, so that thing is 2-. All right, not too messy. So let's do another drawing. Now we're gonna change things up a little bit. And this time, what I'm gonna do is I'm gonna consider another depiction. So we're after a 2- ion. And what I've done here is I've taken an electron pair from this oxygen here, and I've pushed it back toward the sulfur and used it to make a covalent bond. All right, and when you do that, it neutralizes the charge on the oxygen. Good thing to remember, you take that electron pair, you push it towards sulfur, oxygen loses its negative charge in the process, and you get a neutral oxygen. Let's write in the remainders. These are minus, minus, minus. This oxygen is neutral. And that means this sulfur has a +1 charge. Okay, now how do I know this is a neutral oxygen? Well, it makes 2 covalent bonds in this depiction, just like water. And you know that oxygen in water is neutral. Okay, so when you see oxygen with 2 covalent bonds, you better be thinking neutral. 1 covalent bond, negative. 3 covalent bonds, positive. Each time you make a covalent bond like that, you have to change the formal oxidation state, the formal charge. And so this is another one of these drawings. And it turns out that there are 4 of these resonance structures. So you could put this double bond on any one of these oxygens. Okay, and let's do one more. Add another one of these double bonds. So I used a lone pair. I used the lone pair again to make another bond to sulfur here. These guys still have their negative charges. Now sulfur's plus charge has been neutralized. And we have 2 neutral oxygens, a neutral sulfur, 2 negative charges on the 2 oxygens out there. And we're going to say that there are 4 of these resonance structures. Okay, let's do this again. And this time I'm going to go a little off the deep end. I like pi bonds so much. So I'll have to finish my drawing here. Look what I did. I took an electron pair off of this oxygen out here and I pushed it onto the sulfur. Okay, when you push that electron pair onto the sulfur to make another bond, you've eaten up one of those lone pairs out there. You're left with 1 lone pair. Okay, now This looks weird, but bear with me for just a minute. And I'm going to get your question in just a second. Okay, Max? Let's see here. So this guy looks strange, but we're going to go with it. Now, when you make 3 bonds to oxygen, you're 1 more than water. And that means you've sort of given up some charge. So we're going to give this guy a plus charge here. We're going to give this guy a negative charge and this guy a negative charge, just like we always did. And the sulfur now, we're going to give we got to neutralize all these guys and end up with 2- overall. So we need a 2- down here on sulfur. Okay. So lots of stuff going on here. What's the best depiction? Well, maybe I'll just you think about what is the best depiction. I'll take a minute to answer Max's question.
Yeah, how come some of these structures aren't regarded as hypervalent, or are they regarded as hypervalent?
Well, definition of hypervalent is a structure where you have something that exceeds the octet rule, essentially. Okay, and so many of them are. Let's see here, I should be careful about how I say this. So hypervalency yeah, so sulfate is definitely hypervalent, okay, even in the case where it obeys the octet rule, because it's using all 6 of its electrons to make bonds, as opposed to just using 2 of them, which it would in, say, hydrogen sulfide. So, Mac, do you want to ask a question?
Can you hear me? Can you hear my microphone?
Yeah.
Okay.
Sure.
I wanted to try to answer what you were asking, but if you're gonna wait to, I'll wait to. Like the question you were asking about which structure.
Yeah, which is the best structure? Go ahead. Which is the best structure? Go ahead.
So that question, like just based on just like what I think I know, is that I would look for the most reasonable of the resonance structures. So oxygen being electronegative, it's more likely to, it's better to have a negative charge on the oxygen. And then you also have 2 neutral oxygens. So I feel like the third one is the most reasonable, but again, that's just the reasoning I'm using. Yes.
Yeah. So that's a very good answer. There's a couple of ways to think about this, okay? For the purposes of this class and in general, I don't want you to draw structures that violate the octet rule. Okay, and we're going to come back to Mac's idea in just a minute, which is a good idea. But this structure here violates the octet rule. Okay, 1, 2, 3, 4, 5, 6 normal covalent bonds around sulfur. What does it mean to say that it violates the octet rule? Why is this a bad depiction? Bad is maybe the wrong word, but it is not rigorous, because a normal covalent bond, as indicated by a line like that, implies that there is a valence orbital that is available to make that interaction. So that line says something about orbitals being involved in forming the interaction. And as a result, we don't like it anymore, because there are not valence orbitals available to make that interaction. And instead, I want you to consider ionic depictions. So this molecule over here is the best depiction because it obeys the octet rule. And it uses charges to achieve a closed shell depiction. Okay, so we're going to say here that this guy is the best resonance structure. Does not violate the octet rule. Okay. let's do Mac's explanation, and then we're going to come back to the questions. So the structure over here on the right is wacky. Something that, you know, you might see somebody draw in an undergraduate chemistry class that got carried away or something. What's the matter with this guy? Lots of things. It violates the octet rule multiple times over. And then, as Mac pointed out, you have positive charges out on oxygen. Okay, and that's bad because oxygen is more electronegative than sulfur. And so if you were to consider where do the charges want to be, they don't want to be organized in this way. It'd be better if oxygen had the negative charge because oxygen is more effective at attracting electrons to it than sulfur. Okay, so positive charge on the more electronegative atom is bad. Undesirable. Okay. So those are the two ways that I would think about this. The other that might be interesting to consider in some structures is the arrangement of charge overall. You know, consider the charge distribution in this molecule. You've got this like asymmetric distribution of charge. It's sort of polarized here in the middle. It's only on these two oxygens. And then these other two oxygens here are positive. So the charge distribution is wonky. Okay, it'd be better to evenly distribute the charge, considering electronegativity effects. Here you got 4 equivalent oxygen atoms around 1 sulfur. And so this is not a nice way to distribute charge and is also undesirable for that reason. Okay, Rachel, do you want to ask your question?
Yeah, I don't know if this is a silly question, but on the third structure, why are there 4 of those resonances? What are the 4?
Well, let's see here. So if you put the double bond in this position, you can put double bonds here, here, and here, right? And if you move the double bond to this position, you could put a double bond here and here. And I guess if you put a double bond to this position, I've already covered that one, right? Have I gotten them all? No, I could put one additional one here. And then I think that gets them all. So we got 1, 2, 3, 4, 5, and 6. Yeah, so this should be 6. Is that what you get?
Yeah, I was getting more. That's why I was confused.
Okay. Thank you. Yeah. All right. So let's move on and do this again. Oh, sorry, Amir, did you want to ask a question?
Yeah, thank you, Professor. So for the third structure, I was wondering, what if we drew it the way we drew the phosphorus pentafluoride by, for example, putting an extra negative charge on the 2 oxygens on the side, and then putting a positive +2 charge on the sulfur, and then drawing the dashed line?
Like this.
Or doing the same thing with another.
For example. Is that what you were asking? I've stunned him to silence or his internet has died. So Amir's thought to use natural resonance depictions here is a good one. And this is a structure that does not violate the octet rule. It is less desirable to me because of charge distribution, right? You got 2- and 2+. and you have a neutral oxygen, and so it is less contributing than one that doesn't have that charge distribution. So I would say it is less desirable, but a valid structure. Okay. All right. Let's do another one. We're going to do IF4 plus. Wacky. So let's start here with the central iodine. And I'm going to just put some fluorines around it. Fluorines are kind of easy. You get a covalent bond and 3 lone pairs, or you can make them just minus and do the natural resonance theory thing. And I know this guy overall has got to be positively charged. Okay, so here's a neutral fragment. Now I need to make sure that I have the right number of valence electrons. Okay, in each of these covalent bonds, I know that fluorine contributes 1, iodine contributes the other. So that means 1, 2, 3, 4 of iodine's 7 valence electrons has been used. So I have 3 left. And one of them is going to make up the positive charge. In other words, if I were to draw 3 valence electrons here, let's just do that for the sake of it. 1, 2, 3 on iodine. That would get you to a neutral structure overall. It exceeds the octet rule in our drawing, but I know this thing is positively charged, okay? So we don't want to do that. So I need to get to a positive charge. So I'm just going to draw 2 on iodine, and I'm going to stick a plus in here. Now remember, you don't want to draw plus on fluorine if you can avoid it, right? Plus on fluorine means most electronegative element on the periodic table is carrying a positive charge. That's not a good situation. It's not crazy to do that to some degree, as we'll see. But here, iodine is a big fat element and more easily ionized. So we're going to take a positive charge and write it on the iodine. So let's take a look at iodine's situation here. We got 2, 4, 6, 8, 10 electrons around iodine. Each of the fluorines is fine. They have their octets, but we got 10 electrons around iodine. So this guy is hypervalent with 10 electrons in normal covalent bonds. Okay, so this violates the octet rule. Let's try drawing it slightly differently. What are we going to do to fix this situation? What we're going to do we're going to do our electrostatic picture idea. Like this. And I'm going to be a little bit more careful here and try and use the circle to indicate a formal charge and no circle to indicate the actual charge. All right, so there's 4 fluorines, so we're going to say there are 4 of these. And let's do it slightly differently, just for the heck of it. This time, however, what I'm going to do is I don't like that positive charge down there. And I'm going to try one of these out. So I heard that fluorine makes pi bonds using its electron pairs. Okay, so what I've done now is I've taken one of the electron pairs on the fluorine. Instead of a single bond, I'm going to use it to make another pi bond, maximize the bonding, because I like pi bonds. And now I'm in a situation where by doing so, I acquire a positive charge on the fluorine. And we neutralize the positive charge. There used to be a positive charge on iodine. Pushing this electron pair down onto iodine neutralizes that positive charge. Okay. So I just pushed it out there. Got to remember our +1 overall. So this guy has an expanded octet again. And a plus charge, formal charge on fluorine. That's no good. Okay, so this guy here is the best resonance structure. Okay. This violates the octet rule. Just don't draw it. You're going to be tempted to draw them because I have them in my notes. Don't do it on the homework. Okay. I told Ding, if you see octet, any violations of the octet, just mark it wrong. Okay. All right, let's do some hypovalent molecules. Hypovalent molecules, oops. Hypovalent molecules, they're a lot of fun. Carbon monoxide is a winner. Let's try and draw a valence structure for carbon monoxide. Here's one. And some problems here. Oxygen looks okay. Oxygen makes 2 bonds and has 2 lone pairs. That's normal. Carbon has 4 electrons and it used 2 of them to make bonds to oxygen. And there's a lone pair on the carbon to use up all of the valence electrons that it has to contribute. But carbon with 2 bonds sort of looks wonky, right? So total number of valence electrons for carbon and oxygen carbon doesn't have enough. So carbon has got 4 electrons, oxygen's got 6 electrons, you've got 10 electrons total if you want to check and make sure that that is right. Okay. So one of the things you can do here to try and get to a better representation is to give carbon 2 more electrons, because I want carbon to have 8 if I can. So let's maximize the bonding to achieve the octet rule, okay? And so what you can do is take this electron pair and push it over to carbon. And in so doing, you can make a bond. We lost an electron pair in oxygen because it ends up now in this bond that we didn't have before. Carbon still has this lone pair. And now when I count them out, I've got 2, 4, 6, 8, 2, 4, 6, 8. Everything looks good except what's missing?
Formal charges.
Yeah, we need some formal charge. 3 bonds to oxygen, that's a positive charge. Carbon will get a negative charge. Remember, if you start with a neutral thing and you want to generate a positive charge by pushing electrons around, you better get a negative charge somewhere, because overall the molecule is neutral. Okay. So now, if I wanted to calculate these formal charges without actually just sort of doing the arithmetic starting from the neutral fragment, what you can do is envision chopping this molecule in half, splitting those bonds equally, giving one electron to oxygen, one electron to carbon. And if you do that, you're going to end up with an oxygen that's got 5 electrons and a carbon that's got 5 electrons. That's one more electron than carbon starts with in the neutral form, and so that means it has a negative charge. Okay, so you take the structure, split the bonds in half, and then calculate the charge on the atom individually to get the formal charge. Okay, so I'm going to tell you here that this guy is the best resonance structure. Okay, so hypovalent molecules put you in this awkward position where you end up drawing formal charges that are maybe counterintuitive. This is an example. Okay, but it's very important to try and maximize the bonding to get to an octet. And hypovalent molecules like carbon monoxide and boron trifluoride do that kind of thing. There's an empty orbital on the carbon looking for some electrons to get to an octet. Now, sometimes with molecules like this, and in general, making a judgment call about the best resonance depiction is difficult. It's tricky. And, you know, this is a case. Sometimes that is a sign that there are multiple contributors. A resonance picture like this is what a philosopher would call a pure form of its electronic structure. It's like an idealized representation. In fact, real molecules don't care how you draw them, and there are mixtures of different representations. Okay, you might say, you know, what color is Rachel's shirt? Rachel's shirt is gold. And somebody would say, well, no, it's really a mixture of brown and yellow and orange, right? Brown and yellow and orange are, you know, the pure forms of colors, I guess, in this example. And you add them together in different amounts to get to the final representation or the best description. Okay, so we call this resonance structure down here a major contributor. Okay. All right, so it contributes to some extent. Now, a couple of fun facts about carbon monoxide. Carbon monoxide has no dipole moment, or very, very small dipole moment. Okay. And, you know, if you were just to look at the electronegativity of the two elements, you'd say, well, oxygen's more electronegative than carbon, so it's going to attract the electrons toward it. And as a result, you know, there should be a dipole where the negative charge is down there on the oxygen. But because carbon is electron deficient, hypovalent, the hole, the absence of that electron pair in its valence shell, pulls the electrons back. And so is it plus and minus? Yeah, it is plus and minus relative to the neutral atoms. You know, that's counteracted by this electronegativity thing. Okay, so overall, the molecule is roughly neutral. It has a very small dipole moment, and you're sort of somewhere in between. Okay, so if you want to know where the charges are, you have to consider real properties of the substance, not just your imaginations about, you know, where you liked, what the rules are about how to draw the thing. All right. Now, this depiction here, where I've taken my electron pair and I pushed it onto oxygen to form a bond, is an example of what's called a dative bond. Okay, so what's a dative bond? Dative bond is where one of the two partners contributes both electrons to make the interaction. Okay, so oxygen is the guy bringing the electrons over to carbon, both of them, you get a bond, and that bond is a dative bond because both of those electrons came from one of the bonding partners. So let's do another example here before I close up shop. So let's do BF3. It's a good one. Boron. Draw some covalent bonds there. Boron has 3 electrons to begin with. You got 3 fluorines with 9 electrons, with 7 electrons each is 21 electrons. So we have 24 electrons total. So let's fill them in. We're going to take our 3 electrons and make normal covalent bonds to fluorine. We know fluorine is usually just 1 bond and then a bunch of lone pairs to get to an octet. And let's count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There we are. All electrons are accounted for. And one thing you might do here is you might say, all right, well, boron's got a problem. It's only got 6 valence electrons around it in this molecule, and so it's hypovalent. And that tells you that in the valence shell of that boron, there is an empty space. So one thing you can do is maximize the bonding. Let's maximize bonding to achieve an octet. And so how do we do that? Well, we use one of the electron pairs on this, whoopsie. On that fluorine. To make a new bond. And when you do that, you push the electron pair down onto boron. If you were to split this guy in half, count up your electrons, you'd find, oh, I now have a positive charge out here on fluorine and a negative charge on the boron. And there are 3 of these for completeness sake. So we have a positive charge on the more electronegative atom. But that's a good resonance structure, it turns out. And that's, you know, the boron trihalides, they tend to have, they do make some pi bond with the adjacent halogen. And it turns out that pi bonds are really sensitive to the length of the bond, and fluorine is nice and small, and it allows the 2 elements to get close to each other. And so in fact, the pi bonding in that molecule is actually important. And it turns out that boron trifluoride is less acidic than boron trichloride or bromide or iodide because of that. Okay, so it's sort of contrary to what you would expect based on electronegativity differences, and it's because of the bond lengths and the inability of those bigger elements to appropriately make a pi bond with the boron. So That depiction on the right, although it goes against your intuition about electronegativity, is a viable, reasonable way to draw things. It acknowledges the empty hole in the valence shell. Okay. All right. So I'm going to say this is a major contributing resonance structure. And this is just the nature of hypovalent molecules. All right, so I'm going to stop there and we'll continue this discussion next time. And if any of you would like to stick around and ask any questions, I'm happy to spend some time clarifying any of the material we have today, but this will be the end of the notes.
I had a question about boron trifluoride.
Mm-hmm.
Wouldn't it make more sense, at least in terms of electronegativity, to make one of the fluorines negative and then just have the boron have 4 electrons? And I think that would count as having a full shell, because then it would have, or no, that doesn't work. I don't know.
Yeah, remember, we got to get to an octet. That's the goal, and that's because the valence orbitals are sensitive to that nuclear charge, and so we're trying to satisfy that nuclear charge. And you want to fill up the valence orbitals to the best extent that you can, and that means getting to an octet for boron. So the idea where you would pull an electron pair off away from the boron and make one of the fluorines minus, for example, and have like an electrostatic interaction, that makes that situation worse.
That makes sense. Thank you. I just wasn't really thinking that clearly.
Okay.
Thank you so much. Have a nice day.
All right. Bye now. Anyone else?
I had a question from earlier in class.
Uh-huh.
Like at the very beginning of the lecture, when we were going over stuff from last week, you were talking about nickel, and you said that it was D10.
Mm-hmm.
But I thought that nickel was D8. So
Yeah, so it is confusing. The neutral atom has S2, it might even be S1D9, I can't remember. But if you look at the orbital occupation of the neutral atom in the gas phase, it gives you something like S1D9 or S2D8. I can't remember. There are a total of 10 valence electrons for nickel. When you start making complexes out of the transition metals, the d orbitals dominate the bonding. And so people talk about the d electron count of the atom in the complex, and they ignore whether it's S or D. They just attribute all of the valence electrons to the d orbital shell. And so, nickel is not S1D9, it's D10 in that world. So,
even though like the 2 of the electrons are from the S.
Yeah, the orbital ordering changes in the complexes. And so people stop talking about the gas phase electron count because it's too complicated, and it's easier to just focus on how many electrons there are in total. And they call them d electrons because you're referring to a transition metal, and the d orbitals are important in the bonding, and the s orbital generally is this big sphere and just bonds to everybody, so they ignore it. So it's just sort of a formalism issue.
Right. So if you were to draw like a crystal field like diagram with like the d like electrons for like a nickel complex, would you draw 10, like filling the, do you know what I'm talking about? Like when
yeah, you would draw 10. That's right. You would know that nickel has a total of 10 valence electrons that can fall into various places depending upon the molecule. Mm-hmm. And so you would want to make sure that you had 10 in your orbital diagram. But
what if it was like a nickel 2 complex? Then would it have 8?
Then it would have 8. Yeah.
Okay.
Yeah, and we'll get to that shortly. Well, we got to do symmetry first, but
yeah.
MO diagrams are coming.
Okay, thank you.
Yeah. Mac, did you want to ask something?
Hi. Yeah, I just want to ask a real